Lecture 2 on quadratic forms and convexity. A quadratic form of an n by n matrix A is the function f in n variables x1, x2 to xn, which can be written as follows: f equals to x transpose ax, and this is equal to sum as I goes from 1 to n, sum as j goes from 1 to n, aij xi xj, where A is an n by n matrix called the matrix of the quadratic form. Example 1. Find the quadratic form of the matrix A equal to 2, 3, 3, 4. Solution. The quadratic form of A is f equal to x1, x2 times the matrix A times this column vector x1, x2. Multiplying these matrices, this will give us 2x1 squared plus 6x1, x2 plus 4x2 squared. Example 2. Find the quadratic form of the matrix A equals to the matrix consisting of the element 1, 0, 3, 0, 7, minus 2, 3, minus 2, 11. Solution. Here, A is a 3 by 3 matrix. So the quadratic form will be a function of 3 variables x1, x2, and x3. So the quadratic form of A is f equal to x1, x2, x3 times A times the column vector x1, x2, x3. Multiplying this will give us x1 squared plus 6x1, x3 plus 7x2 squared minus 4x2, x3 plus 11x3 squared. Example 3. Find the quadratic form of the matrix A equal to the matrix consisting of the element 1, 2, 4, minus 5. Solution. The quadratic form of A is f equal to the row vector x1, x2 times the matrix A times the column vector x1, x2. Please note A is a 2 by 2 matrix, so our quadratic form will be a function of 2 variables x1 and x2. So multiplying this out will give us f equal to x1 squared plus 6x1, x2 minus 5x2 squared. Example number 4. Find the quadratic form of the matrix A equals to the matrix of the element 1, 3, 3, minus 5. Solution. Again, here the matrix A is a 2 by 2 matrix, so the quadratic form of A will be a function of 2 variables x1 and x2. That is, the quadratic form of A is f equal to the row vector x1, x2 times the matrix A times the column vector x1, x2. Multiplying out will give us f equal to x1 squared plus 6x1, x2 minus 5x2 squared. So in view of examples 3 and 4, we note that the matrix of a quadratic form is not unique. However, if we restrict ourselves to symmetric matrices, we find that the matrix of quadratic form is unique. Definiteness of quadratic forms. A quadratic form is said to be positive definite, that is, x transpose ax is greater than 0, if the matrix A of the quadratic form is positive definite. A quadratic form is said to be positive semi-definite, that is, x transpose ax is greater than or equal to 0. Please note semi-definite in the sense that we have greater than or equal to here. It was positive definite because it was strictly greater than 0 here. So a quadratic form is said to be positive definite if the matrix A of the quadratic form is also positive semi-definite. A quadratic form is said to be negative definite, that is, x transpose AX is strictly less than 0 if the matrix A of the quadratic form is also negative definite. A quadratic form is said to be negative semi-definite, that is, x transpose AX is less than or equal to 0 if the matrix A of the quadratic form is also negative semi-definite. Let us now consider the concept that will help us to determine the definiteness of a square matrix A. First, we consider what we meant by the kth principal minor of a matrix, denoted by dk. A kth principal minor of an n by n matrix is the determinant of any k by k submatrix obtained by deleting n minus k rows and corresponding n minus k columns of the matrix. For example, that's example number 5. Consider the matrix A consisting of the element 1, 0, 3, 0, 7, minus 2, 3, minus 2, 11. The first principal minors of A are obtained by deleting any 2 rows and 2 corresponding columns of A. Note here n is 3, that is, the matrix is a 3 by 3 matrix, so we are deleting any n minus k rows and columns. Here, considering the first principal minor, that means we are putting k equals to 1. So 3 minus 1 will give us 2. We are deleting any 2 rows and corresponding 2 columns of A. Here is our matrix A. Let us delete row 1 and row 2 first. If we delete row 1 and row 2, we also delete column 1 and column 2. This is column 1 and this is column 2. So we are left with 11. So that is the first principal minor of A. So we have D1 equals to 11. Now let us delete row 1 and row 3. If we delete row 1 and row 3, we also delete column 1 and column 3. Then we have D1 also equal to this 7. Next, we delete row 2 and 3. This row 2 and this row 3. We also delete column 2 and 3. This column 2 and this column 3. And this will also give us D1 to be equal to this element 1. So we notice that for a 3 by 3 matrix A, that the first principal minor of A are the leading diagonal element 1, 7, and 11. Now let us obtain the second principal minors. The second principal minor of A are obtained by deleting any 1 row and corresponding column of A. Here for the second principal minor, we are putting k equals to 2. So n minus k will be 3 minus 2, which is 1. That is why we are deleting 1 row and 1 column. This is our given matrix A. So let us delete row 1 and column 1. Deleting row 1 and column 1, so we are left with this submatrix. So that will give us D2 is the determinant of that submatrix, which is equal to 73. Again, if we delete row 2 and column 2, This is row 2, column 2. We are left with this D2 equals to the determinant of the submatrix 1, 3, 3, 11, and that will give us 2. Next, if we delete row 3 and column 3, this will give us the determinant of this submatrix D2 equals to 1, determinant of 1, 0, 0, 7, and this is equal to 7. So for this 3 by 3 matrix, we observe that we also have the second principal minor of the matrix A to be what we have obtained. And finally, the third principal minor of A is obtained by deleting no row and no column of A. That is, here we are putting k equals to 3. So we are subtracting n minus k, which is 3 minus 3. 3 minus 3 is 0. So that means we are deleting no row and no column. So therefore, the third principal minor of A is the determinant of A itself. And this will give us 10. Next, we consider another concept called the kth leading principal minor. That's the leading principal minor of the matrix. So we denote this by delta k. We define the kth leading principal minor of an n by n matrix as the determinant of a k by k submatrix obtained by deleting the last n minus k rows and the last n minus k columns of the matrix. Please note the emphasis here is on the last rows and the last columns, not any rows or any column as in the case of principal minor. Example 6. Again, let us consider the same matrix as before, the matrix A. Let us compute the first leading principal minor of A. The first leading principal minor of A is obtained by deleting the last 2 rows and the last 2 columns of A. This is our matrix A. Deleting the last 2 rows, that's we are deleting row 2 and row 3 and column 2 and column 3. So deleting row 2 and row 3, we also delete column 2 and column 3. So this will give us our first leading principal minor to be delta 1 equals to 1, equals to this one. Next, the second leading principal minor of A is obtained by deleting the last row and the last column. Here we are putting k equals to 2, that is 3 minus 2 is 1. So we are deleting the last row and the last column of A. This is our matrix A. So deleting row 3 and column 3, this is row 3 and this is column 3. So we are left with this submatrix 1007. So this will give us the second leading principal minor, delta 2, to be the determinant of this matrix, which is equal to 7. Then the third leading principal minor. The third leading principal minor of A is obtained by deleting no row and no column of A. That is, it is the determinant of A itself. So the determinant of A, which is delta 3, will give us a 10. Definition. A square matrix is positive definite if and only if all its leading principal minors are positive. That is, if delta k is greater than 0 for all k. A square matrix is positive semi-definite if and only if all its principal minors are non-negative. That is, dk is greater than or equal to 0 for all k. Definition. A square matrix is negative definite if and only if its kth non-zero leading principal minor have the same sign as minus 1 to power k. And it is negative semi-definite if and only if its kth non-zero principal minor have the same sign as minus 1 to power k. Definition: the function f of lambda equal to the determinant of a minus lambda I, where lambda is a scalar and I is an identity matrix, is called the characteristic polynomial of the matrix A. The values of lambda satisfying the characteristic equation f of lambda equal to 0 are called the characteristic root or eigenvalues of A. Definiteness in terms of eigenvalues. A square matrix is positive definite if and only if all the eigenvalues are positive. That is, if all the lambdas are greater than 0. And a square matrix is positive semi-definite if and only if all eigenvalues are non-negative. That is, lambda is greater than or equal to 0. A square matrix is negative definite if and only if all the eigenvalues are negative. That's lambda less than 0, strictly less than 0. And a square matrix is negative semi-definite if and only if all eigenvalues are negative or 0. That is, lambda less than or equal to 0. A square matrix is indefinite if none of the above conditions hold. The Hessian of a function. Let f of x1, x2 to xn be a function which has a continuous second order partial derivatives. Thus, we assume f to be a smooth function. Then, an n by n symmetric matrix H, defined as follows: H of x1, x2 to xn equal to Fij, where f of ij equals to second partial derivative of f with respect to xi with respect to xj for I and j going from 1 to n, is called the Hessian of f. Hessian and convexity. The Hessian of a function f can be used to determine whether f is convex or not, as given in the following theorem. Theorem number 2. If a function f has a continuous second order partial derivatives at each point x in a convex set S, then a. f is convex if and only if the Hessian H of f is positive semi-definite at each point x in S. B. f is concave if and only if the Hessian H of f is negative semi-definite at each point x in S. Example 7. Form the Hessian of the function f equal to x1 squared plus x2 squared plus 2x3 squared minus x1 x2 minus x2 x3 minus x1 x3. and hence determine whether F is convex or concave or non-convex. Solution. Given the function f equal to x1 squared plus x2 squared plus 2x3 squared minus x1 x2 minus x2 x3 minus x1 x3, we differentiate f partially with respect to x1, and that will give us 2x1 minus x2 minus x3. Since there is no x1 here, the derivative is 0. Derivative of this term is 0. Derivative of this term is 0. Next, we differentiate f partially with respect to x2. So the derivative of this is 2x2. There's no x2 here. There's no x2 here. So the derivative is 0. The derivative of this term with respect to x2 is minus x1. The derivative of this term with respect to x2 is minus x3. And there's no x2 here. So partial derivative with respect to x2 is 2x2 minus x1 minus x3. So differentiating partially with respect to x3, this derivative of this term is 4x3 minus derivative of this term with respect to x3 is minus x2. Derivative of this with respect to x3 is minus x1. So this will give us 4x3 minus x2 minus x1. Now differentiating this one with respect to x1, derivative with respect to x1 will give us these 2. Differentiating this one with respect to x2, derivative of this with respect to x2 will give us 2. And differentiating this one with respect to x3, derivative with respect to x3 will give us 4. Differentiating this one with respect to x2, that will give us f21. With respect to x2, that will give us minus 1. Or if you differentiate this one with respect to x1, that will give us f12. And derivative with respect to x1 will be equal to minus 1. So f21 is equal to f12 equals to minus 1. Next, if you differentiate f1 with respect to x3, that will give us minus 1. Or if you differentiate f3 with respect to x1, that will also give us minus 1. So f31 is equal to f13 equals to minus 1. And finally, if you differentiate f3 with respect to x2, that will give us minus 1. Or if you differentiate f2 with respect to x3, that will also give us minus 1. So f23 is equal to f32 and is equal to minus 1. So therefore, our HESSIAN metric H is equal to f11, which is 2, f12, which is minus 1, f13, which is minus 1, f21, which is minus 1, f22 is 2, f23 is minus 1, f31 is minus 1, f32 is minus 1, f33 is 4. Now the first order principal minors of our HESSIAN metric H are the determinant of the submatrices formed by deleting any 2 rows and corresponding 2 columns of H, and that will give us deleting the first and the second row, the first and the second column of H. We will obtain the first order principal minor to be 4. If you delete the first and the third rows, the first and the third column of H, that will also give us the first order principal minor to be 2. And if we delete the second and the third rows, the second and the third column of H, and that will also give us the first order principal minor to be 2. The second order principal minors of H are the determinant of submatrices formed by deleting 1 row and 1 column of H. That's any 1 row and any 1 column of H. So deleting row 1 and column 1 of H, we obtain the second order principal minor of 7. Deleting the second row and the second column of H, we also obtain the second order principal minor of 7. And deleting the third row and third column of H, we obtain the second order principal minor of 3. Now, the third order principal minor of H is the determinant of H itself, and that will give us 6. So we have seen that the Hessian H of F is positive definite, since all its principal minors and hence the leading principal minors are positive. So the function f is convex. On your own, investigate the definiteness of the following matrices. 1. The matrix A consisting of the element 1, 2, 4, minus 5. 2. The matrix B consisting of the element 1, 3, 3, minus 5. 3. The matrix C consisting of the element 5, minus 3, minus 3, minus 5. And 4. The matrix D consisting of the element minus 3, 2, 2, minus 5.